All right, Surabhi, welcome to your final thesis presentation. You'll have 40 minutes to present. After that, there'll be time for question and answer. And following that, Professor Fleming and I will briefly leave the room to discuss how well you've done. And when we come back, we'll give you the results. So just to remind everyone, if you can, while presenting, to mute yourselves and turn off your cameras for bandwidth issues. And Surabhi, you may start whenever you're ready.
Okay, thank you, Rob. Good morning, everyone, and thank you for joining me today for my thesis defense. And my topic is Impacts of Building Circularity on Carbon Emissions, a Statistical Life Cycle Assessment of a Greenhouse. I would like to start my thesis defense with what has inspired me to be in this field of sustainability and caused me to take up this master's course. During time in India, I took up a couple of projects that were based in rural areas and urban slums. Working in those areas made me see directly the externalities of urbanization that are usually not seen by people and that burdens only a certain section of the society. Whether it is climate change or whether it is COVID-19, there are only going to be certain sections of the society that will be seriously impacted by it. Today, you must have all heard that we are all in the same boat, but that's not true. We might be in the same storm, but we are not in the same boat. For some, quarantine is optimal, moment of reflection, of reconnection, easy, in flip-flops, with a whiskey or tea, and for others, it is a desperate crisis. And each one will emerge in his own way from that storm. Some with a tan from their pool, and others with scars on their soul. My heart goes out for people who aren't able to afford the same life as me, and I will always in my professional life work to make a positive impact for these people. Being an architect in the field of sustainability, I have attempted to study the impact of our practices on climate change. However, whatever your position is on climate change, there can be no doubt about humanity's overuse of world's natural resources. As a society, we must move away from this take, make, and dispose mentality. And as members of construction industry, it is our duty to take on this challenge. It is our responsibility as designers and engineers to consider circular economy principles and material selection from the very beginning of the design process of our projects. This will require a change in how we work, what materials we choose, and how we influence our clients' material choices. So through my thesis, I'm trying to validate that by adapting to circularity design principles, the resultant building will have a lower embodied carbon footprint without negatively impacting the operational carbon savings. The issue of global warming is both urgent and essential, as the emissions that will be released in the next couple of decades are going to be very critical in keeping the global temperatures at a manageable level. The average temperature has already increased by 1 degree Celsius compared to pre-industrial levels, and even this change has exacerbated the extreme weather events, caused color bleaching of coral reefs, and has caused large chunks of glacier ice in the Antarctic to start breaking apart, while prolonging wildfire periods. To have even a 67% chance of keeping our temperature below 1.5 degrees Celsius, which is the Paris Climate Agreement goal, the industry can only release about additional 340 gigatons of carbon dioxide into the atmosphere between now and 2030. This upper limit is called the carbon budget. These statistics indicate that the industry practices need to change immediately to meet the climate goals and ensure that our planet remains a habitable place for future generations. If we don't do this, then these reinforcing processes will set an irreversible chain reaction, which will be beyond human control. The built environment industry fuels global warming and is thus a critical component in the efforts to reduce overall carbon dioxide emissions. At 39%, the built environment is the single most significant contributor to global carbon dioxide emissions. This trend is expected to accelerate as the population grows and people migrate to the cities. There are two ways in which buildings contribute to the carbon emissions. Embodied carbon is the carbon that is released in the manufacturing, production, and transportation of the building materials, whereas operational carbon is the carbon load created by the energy used to heat and power a building. And the total carbon emissions associated with a building is the sum of both embodied and operational carbon. In extant investigations, focus is primarily given to the efficiency in operational carbon spending, while overlooking the embodied emissions of buildings. However, owing to the technological advances, the efficiency and capacity of renewable energy sources that are expected to increase, allowing the industry to significantly reduce the operational carbon per square foot of construction, even after adding 30 billion square foot of building stock. Embodied carbon coming from the new construction, on the other hand, if not addressed, will comprise 90% of the total carbon emissions by 2050. So we can no longer keep using high embodied carbon materials and wait for long-term operational savings to kick in. We will have to balance both operational and embodied carbon emissions in our design processes. One of the greatest obstacles to the reduction of embodied carbon of buildings are the current economic practices. The need to increase the GDP has prompted many countries to adopt to a linear economic practice comprising of take, make, and waste steps. While this economic model improves GDP, it does not take into account the fact that Earth is a planet with finite resources, and it will not be able to sustain itself if perpetual growth is our guiding principle. A shift to circular economy practices mitigates the problems created by the linear economic system. The circular economy is based on the principle of waste equals food, and the end of life is connected to production by the recycling sector. Adoption of this framework can significantly reduce greenhouse gas emissions across the economy through strategies that reduce emissions across value chains, retain embodied energy in products, and sequester carbon in soil and products. However, to switch from linear economic model to circular model, several issues must be overcome. These issues include transparency of manufacturing processes, requiring collaboration and partnerships between a lot of stakeholders, and the need of new business models that are planned to gain profit from these circularity practices. Profit is the big word here. Profit drives all the decisions. So I asked myself, what do companies care about? Money, obviously. But in the US, the biggest carbon emitters are also required to report their carbon footprint. So companies also care about carbon. Thus, it would be beneficial to evaluate the carbon savings of such circular design strategies. In order to successfully investigate the topic, I needed a real architecture project that used the majorly used building materials in the country. I would like to thank Revision Architecture for collaborating with me and letting me use one of their ongoing projects for this study. It is a head house greenhouse project where the head house is like a workshop where they put the plants together and then grow it in the adjacent greenhouse. This is a rendering of the head house building. I used a set of guiding principles and goals that would guide my project through the design process. And they are for performance, building elements and materials that make the shearing layers of structure and skin of the building elements should be low carbon emitting materials and last as long as possible. On the left, you can see how it can last as long as possible in the material chain. I used, for systems, the building system should be designed in terms of shearing layers that have different life cycles and should be easy to reuse, remanufacture, recycle, or repurpose. culture follow a process that requires high engagement with all stakeholders of the project and transform a culture of wasteful design decisions to efficient material choices. And for experience, inspire all stakeholders to do good by achieving a challenging and unprecedented goal, resulting in a feeling of accomplishment. Now the goal. The performance will be evaluated by the amount of carbon savings. For this, I use the goals set by Architecture 2030 and Carbon Leadership Forum. For Architecture 2030, they require buildings to offset 100% of their operational carbon and 70% of the total carbon emissions by 2030. In another goal set by Carbon Leadership Forum, they require the building to offset 65% of the embodied carbon emissions by 2030. These goals can be achieved in 3 ways: reduction from the baseline, on-site or off-site renewable energy offsets. However, off-site renewable energy offsets cannot be more than 20%, and by carbon sequestration on-site. For systems, I set a goal for myself to divert at least 80% of the demolition waste at the end of life by using principles of design for disassembly. This was done taking the reference from LEED that requires 75% diversion of demolition waste, and I just wanted to do a little better than them. For culture, discuss circularity and its principles with the architects of the project to spread awareness about the effort. And for experience, I just wanted to master the understanding of circularity, which is a rare practice, to be able to implement it professionally. But these are the quantifiable goals that you see on the screen. The next step was to get an inventory of all the materials that were used in the building and find out the global warming impact of primary production, manufacturing, transportation, and end of life of these materials. Luckily, we have BIM tools like Tally, Athena, One-Click LCA in the industry now that have made this very tedious job quite simple. For this project, I have used Tally as the databases are based in US and hence more precise and reliable. The video shows the process of how easily I was able to do this once I had a Revit model. A life cycle assessment can help in many ways. Life cycle assessments are one of the most effective ways to evaluate how a product will impact the environment. In the green building industry, an LCA has two primary benefits. It helps designers to make more informed decisions during the design and building processes. It drives innovation by revealing opportunities for manufacturers to improve a product's efficiency and quality. So in the video, you can see that I'm assigning all the materials, and I need to do so till all the categories are green. And all these categories need to be filled to extract a report. And the scope of the building is limited to the structure, foundation, and enclosure of the building. And the goal was to benchmark the carbon emissions of the building. Once that is done, I can save a report. And that gives me a report like this with so much of data and charts, which are very helpful. It also gives me a life cycle inventory information where I can see what was the life cycle of that material, how long does it last, and what's the end of life scope of the material. And that is given for all the materials. There's also this Excel that comes out of it with a lot of data and with pivot tables so you can filter data the way you need it. and it has impact. It doesn't just have global warming potential, it has several other impact categories like eutrophication, acidification, non-renewable energy use, and a lot of other data. So coming to the baseline, the operational carbon from 2020 to 2030 is 76,276 kilograms carbon dioxide equivalent. The operational carbon values are adapted from the energy modeling that Stengel Engineers has done for this building with some of my own energy analysis. The embodied carbon is almost the same as 10 years of operational carbon at 720,710 kg CO2 equivalent. So the total baseline emissions are around 1,500,000 kg CO2 equivalent. And then the total waste diverted was also retrieved from tally, and it was found to be 87,000 kilograms. These numbers make up to 48% of the materials that are being diverted. And for the rest of the categories, baseline is considered to be at 0% savings, as the reductions are to be made in reference to the baseline. Further, step by step, we will go through on-site renewable energy offsets, followed by 3 carbon reduction measures, followed by strategies for carbon sequestration on site, and off-site renewable energy credits. As you can see on the site plan, the south side of the roof is designed to hold a PV array of 155 kilowatt, which will produce 20% more energy than the total energy required in the operations of the building. Right here with this installation, we offset 120% of operational carbon, already meeting the 2030 goal for operational carbon. And it also results in almost 61% decrease in total carbon emissions. And for the extra 20% credits from the operational carbon, we can use those offsets to, for reaching our goal for embodied carbon. Now, the baseline life cycle assessment results indicated that 82% of global warming impact is coming from production and end of life, which really builds the case for adopting to the circular economy principles, where we are trying to reduce the impact of both these processes by tying them together with the recycling sector. We can also see that 72% of the impact is coming from concrete, which is cast in place concrete, and regular concrete masonry units used in the buildings. And glass, which is used in the greenhouse. These metrics are great as it guides the designer where they need to focus their efforts on. So that's exactly what I did. Cast in place concrete was used for slabs and foundation walls. It is not the best material for circular economy. And the concrete I modeled in tally has 49% slag composition, which is quite good, but still its impact is quite high. The impact of regular concrete using no cement alternatives would be even higher. In addition, it uses high volume of material of concrete and reinforcing steel. After the end of life, it can only be broken down into aggregates. According to the standard industry practice, only 55% of the concrete is downcycled into aggregates. 45% of it still ends up in the landfill. The construction process generates waste from excessive concrete, formwork, bracing, packaging, debris that accumulates on cast-in-place sites. In a linear economic practice, raw materials are first used to produce cement, which is then used to produce concrete, which is then used to the end of life of the building, after which 55% of it gets downcycled into aggregates and 45% go to the landfill. So I propose to replace these slabs with precast concrete slabs or slab components and the foundation walls with interlocking CMU. In addition to this, I also replaced the regular CMU used in the wall construction with interlocking CMU. Using interlocking CMU negates the need of using mortar and reduces the amount of steel required for reinforcement. Here's how it will look in a circular economy. Cement, recycled aggregates, and other cement substitutes, which are secondary materials from other industrial processes. For example, fly ash is a secondary material obtained as a byproduct of coal combustion. So all these materials are used to make precast components like masonry units and slab components, which will be used till the end of its life, either be reused in another building as the same component, or part of it will be turned into aggregates that can be recycled back into these precast products. This carbon reduction measure shows a further decrease of 16.8% in embodied carbon emissions and 8.3% decrease in the total carbon emissions. By this, we've also achieved the waste diversion goal. The next category to focus on was glass. Now, why glass? Glass is strong, long-lasting, and 100% recyclable material by property, right? So it is a very circular material, even if it has a higher embodied carbon. So what? Why would it be a problem for the circular economy? The fact is that almost 0% of architectural glass gets recycled back into architectural glass. And a very little portion of architectural glass gets recycled at all in road products or landscaping products. This is a classic example of our linear industry practices that need change. 0% recycling for 100% recyclable material, in my eyes, is a huge failure and a missed opportunity of the construction industry today. Today, the world is facing sand scarcity due to the high demand of the building sector. Recycling and reusing both concrete and glass can also reduce burden on natural resources like sand. The reason why glass is not recycled is because they are laminated for safety, and they have different coatings which make their melting points really high and almost impossible to separate the layers and be recycled. In a linear economy, raw material will be used to manufacture glass, which is then processed, after which it will be used to manufacture insulating units for construction and landfill at the end of life. Switching to the circular economy will challenge the way we maybe tint the glass. For example, colored interlayers could be added in the glazing assembly to mimic tinted glass, and open markets and room for innovation for recycling businesses that would provide delamination services. In a circular economy, a specialist contractor will be an additional stakeholder that will supply and collect glass from the building owner before and after the use phase of the building. The glass that cannot be recycled back into architectural glass will be recycled to manufacture container products, and only remaining low-grade glass will be downcycled for applications like glass vault. Energy will be recovered during the melting processes, only after which the last of the waste would be sent to the landfill. Preferably first, it will be maintained. If not, then reused or redistributed. If not that, then refurbished or manufactured and then recycled. And if none of it is possible, then the energy will be recovered by the end of life processes before it gets sent to the landfill. This is only possible if many of the industry practices are shifted. But even today, the glass windows can be salvaged to reuse into greenhouses. When we reuse a material, the impact associated with it becomes half as the life becomes double. When this is done, there is an additional saving of 8.2% of embodied carbon and 3.7% of the total carbon emissions without any impact on operational carbon. So with this, we have also achieved our total carbon, the reduction in the total carbon emission goal by Architecture 2030. But let's go back a step and try another option. Another product evaluated for replacing the glass was acrylic plastic sheet. The acrylic plastic sheet is a lightweight material quite similar in structure to polycarbonate sheets that are widely used in greenhouse applications. This product has half the embodied carbon as virgin glass and as a little more embodied carbon, and it just has a little more embodied carbon than salvaged glass. It is up to 75% recyclable through the process of reverse polymerization. This extruded plastic product can be turned back into its original polymer known as MMA. However, due to its better thermal insulation and light transmitting properties that is suitable for a greenhouse, there are also operational savings to using this product. This scenario was also modeled by Stengel Engineering, and in a separate study conducted by me, a 5% drop in the energy use was observed by switching from glass to acrylic cellular plastic. This results in 2% higher total carbon savings than glass, as well as 5% more on-site renewable credits that can be counted towards embodied carbon reductions. Now, if all the joineries are well documented and made using dry construction techniques, it will be very easy to disassemble the greenhouse at the end of its life. Since volume-wise, it is very little in comparison to concrete, only a little savings can be seen in the waste diversion. So, through my thesis, by switching to the circular architecture design principles, substantial embodied carbon savings can be generated without negatively impacting the operational carbon savings. Now I'll validate the solutions in terms of guiding principles and goals. All the choices that are taken to keep the materials and material loop for the longest possible time and have low embodied carbon. By reducing the use of raw materials, maintaining the product well, reusing the product in its current stage and remanufacturing it. Even though we looked at only 2 building materials, these 2 materials make the majority of mass of building. And by tackling these materials, we would be able to divert a majority of this mass from the landfill. Material choices will also allow designing in different shearing layers that stand on their own. If architects could start thinking about end of life while designing the building, like we did in this process, it can drastically change the work culture, requiring more innovation and collaboration, and will give drastically better results. The quantifiable goals are achieved by this project, which are very high goals given the current industry practice, and would set an example for the architects for the entire nation. This indeed is a matter of pride for all the stakeholders if done. So these were our baseline emissions. Which were brought down considerably by offsets and carbon reduction measures. The diversion was more than 90%. The operational energy was offsetted. The total carbon emissions were brought down by 75%, and the embodied carbon emissions were brought down by 48%. And I met 3 of the goals set by Architecture 2030 and the LEED standards. However, the embodied carbon emissions goal by Carbon Leadership Forum was not met. However, we have not completely lost the opportunity. We still have the off-site renewable energy credits that we can claim for 20%. And if we do that, if we buy credits, then yes, we can still achieve the embodied carbon goal. And this way we would have achieved all four goals. But say we don't want to use the off-site energy credits, because that is usually the last option, and it's a shortcut. So when will the building become carbon neutral? By 2050, owing to the continued PV savings, only about 10,700 kg CO2 equivalent carbon remains to be offset. This much carbon dioxide can be easily sequestered if only 23 trees were planted on the site in 2020 while making the building. Thus, the building will be carbon neutral by 2050. And by the end of its life, the building will be carbon negative. And after the end of its life, there will be 136,000 worth of credits that can be used by building or buildings that reuse the materials disassembled from this building. They're just credits that can be used further. So they're not really savings. There are also certain potential studies that I have a keen interest on pursuing further. The next material category that was coming up as a high contributor is the thermal insulation. It would be interesting to study thermal insulation and strategies to reduce its impact using these principles. Weatherproofing is one of the barriers to circular wall assemblies and will be a good next step to study. Another thing, I would have loved to use the MCI calculator, which is the material circularity index calculator that comes along with one-click LCA that actually measures the circularity of the building materials. However, it was not available on student version, so I wasn't able to do it. And with this, I would like to end my presentation and would like to take this opportunity to thank Rob Fryer for all your valuable inputs throughout the thesis, even on Sundays. Thanks for letting us choose our own paths, and thank you, Professor Rob Fleming, first of all, for connecting me with revision or to gain access to this project, but also because you believed in me when I didn't believe in myself. I owe some of the best moments of my professional and academic life to both of you, and I'm really sad that next semester I won't be a part of MSSD. But they say a good beginning lasts a lifetime, and I hope I'm able to give back to the MSSD community one day and hope to make you both proud. Thank you.
Right, thank you. All right, so this is the time for questions and answers. I'm sorry, any clarifying questions? Sorry, I'm distracted with getting the time down.
Yes,
Are there any?
Yes, on slide, sorry for being so specific. Module D on slide 49, I didn't know what a module D was. Do you know what a module D, Surabhi, can you tell me what module D was?
Yes, so say concrete is then converted into aggregates at the end of life. So all the energy that is required to convert a concrete into aggregates is also burden.
Yeah.
So that burden also goes on
Thank
this
you.
project. So all the recycling and reusing energy and all the carbon emissions associated with end of life that is not landfill is going there.
Thank you.
I have one clarifying question.
Yes, please go ahead.
I know it might be maybe impossible to figure out, but have you considered the carbon sequestered from the greenhouse plants that you're growing? Because within all of that, all of the dried plant material is roughly 50% carbon. So that's probably not insignificant over the life of the building. Something to think about.
Yeah.
That's a great idea.
Yeah. There's actually a tool called Pathfinder, which you can use to calculate the carbon sequestration by your landscaping.
Really?
And yeah, so
What's it called?
I hope to use it someday. It's called Pathfinder, Path Finder.
I'll check that out.
Any other clarifying questions?
Nope.
Okay, cautions.
I think Abhi had one.
Oh,
Okay, I was just curious to ask you the ACP sheets when you have run it into Sapphira. So it also shows overheating and I think there is excessive light. So how was that considered? And how did it actually help in getting down the reduction to 5%?
So I just used the SHGC, VT, and U values. That's all I had from the report. So it was a complex process of how I came up with the operational emissions. There was a report, the emissions for ACP was already done by Stengel Engineering. I had to find out the emissions for glass. So I was going reverse. So then what I did was, and all the information that I had was these three, U value, SHGC, and VT. And then what I did was I kept the HVAC constant and just changed these three values for acrylic sheet. It has a better thermal resistance to what I understand as compared to glass, which makes it better.
all right, thank you. Let's move along to cautions.
Well, first up, this is a very technically complex presentation to deliver with a lot of numbers, and so great job on that. I know we're doing cautions, but I just want to, before I do any cautions, I just want to acknowledge the difficulty level of what you're trying to accomplish. And that is going to be part of your career, is explaining these things. I'm just looking at my notes here. So only a couple of cautions, really. I guess I would have liked to see, and maybe you could put in your paper, and mention of technical and biological nutrients in your, what I call a figure 8 diagram, where you have the two circular. Be nice to just acknowledge those terms a bit, just because I think a lot of people can understand that. You could do that in your paper, though. You don't have to. That's my first one. Somebody else can go.
I just had a caution about the countdown you had on the right side of the screen. When you took a step, when you say, here, I'm going to take a step back, it would be good if you showed somehow like a ghost of where it was when you looked at that, so we could compare the different ones, right? So
Yeah,
if you
I wrote that.
Yeah. And to say maybe at the end, because you still only had your goals at the top, but you didn't say what you achieved. So it would be good if you just added, like, you know, I had 75%. Yeah, if you could go to that in your conclusion, that last one. Yeah, here. So
Right, the percentage.
like the column of 70, under 70, maybe down right near where the green bar for that one is, say just rate 75%.
Yeah,
so what you
I
actually
agree.
achieved.
Right.
Well, and I would also, I think that I like the chart on the right. It's like a bank account that you're giving us a story about. I like to see a little line at the previous level.
Yeah.
Just a little horizontal line of where you were and then where you got to, because it's hard to, I just magically saw these bars go down. I wasn't sure how much, and it looked great, but I wanted to know more about that. The other thing that I think I would like to see you do, and I'm sure you do this in your papers, explain design for disassembly. There was a lot of assumptions made, and probably correct assumptions, that would be a good approach, but I think you should lay that out a little bit more. I think that's a pretty radical concept for most folks. I really like the tensioned, is it post-tensioned slabs? What is it? Post-formed slabs, what did you call it? That was an interesting concept, to actually pre-make your slabs and bring them in rather than pouring. Gives you a lot of, I'm sorry, we're not on optimisms yet. But I do think you need to lay out design for disassembly a little bit more in your verbal, not for this, but for your paper, which I'm sure you did. And also, I think you need to explain what slag is. I know that, and I think maybe rather than actually making these cautions, if you identify your audience, like, so for example, if you're presenting back to revision, you don't have to explain all those concepts. If you're presenting to a broader audience, you might have to explain some of these things of what they are, or just have it in the corner for people that don't know, they could see that.
Or I had to make a lot of assumptions of what my audience would know.
Yeah, you did. You did. And that's fine. That's fine. I have lots of little other minor cautions, which I don't need to talk about here because I just don't have to do that. So
All right.
I'm
Are
done
there
with
any other cautions? Yep. Go ahead, Biri.
It is more of a suggestion. So the materials that you are replacing, it might be nice to also mention the trade-offs, because definitely even if there is a reduction in carbon,
Right.
there must be some other properties which are
Right. Which is in my paper, I recognized it as something that for example, if I'm recommending plastic, then there are a whole lot of things that come up with the end of life of plastic, which I have not really done in my paper, which was really out of the scope of my thesis right now, but which can be done in the future, that I can evaluate other environmental impacts of I currently have just looked at global warming potential, even from the results that I got from Tally. But there are so many other environmental impacts, and it would be a good idea to look at the overall impact in different categories.
I have a question. In the beginning, when you were saying something about your goal was 80%, is that the orange column right there?
Yes.
Did you say that the other goal was 70%, but you wanted to aim for 80?
Yes. So LEED requires you to divert waste by 75%. And I just wanted to do a little better because LEED is not really looking at circularity. And if I'm looking at circularity, then I should do more.
Right. I'm just curious why you stuck with the 80 if you didn't accomplish the 80. Like your goal, like your orange looks like if you stuck with 75, you would have accomplished it.
So this is part of the confusion here, why you need to write the number down. But she actually exceeded 80, but you can't tell.
Oh.
Because.
Gotcha. Okay.
Yeah.
Sorry.
Yeah.
All right. Graphic design. It all matters. It all matters. So.
Okay. So I'm not seeing any other cautions because I can't actually see everybody at once on my screen. So unless someone speaks up, let's move to optimisms. And I would just like to start by saying, wow, what an improvement from your practice presentation. And I'll add more onto this later, but I just wanted to say this is like 500% better than the practice presentation. So
5 times better.
At
Sorry,
least.
I missed the practice. I wish I had seen the practice now. Naranjan had his hand up.
Go ahead, Naranjan.
So, yeah, the video that you shown was really helpful and was really good to understand the entire process and the options. Yeah, that's really cool. And the entire presentation was clear. Good.
I see a lot of nodding heads seconding that. Yes.
Yeah, I just want to say great job making this all clear and presented in sort of an appealing way, because I know LCAs can get a little dry after a while. You did a really good job.
Surabhi, congratulations. It looks so good.
Thank you.
You did so much work in the last week from your practice presentation. Like your storytelling really came along and it really helped. I was engaged the whole time.
Wow.
I think your problem explanation was really great, and the way you sort of drew us into the scenario that we are currently in, it was well done. Yeah.
Yep. I would absolutely agree to that. It was quite enlightening. and I am still in the process of learning about this topic. So I think it was overall it was really great. Great job.
Hello, Surabhi. This is
Hi.
Aguila. So I like how you sympathize with people suffers, with people problems, how you sympathize with them, how you have passion to make change, how you have passion to save the people in your country. So I think this is the mean of sustainability, to have empathy with people, to feel about people. So thank you for that. Thank you for sharing with us your empathy with your people, how you, and show us how much you are sympathize with people suffers. So thank you so much.
Professor Fleming?
Okay, I have a number of optimisms. I'll be a little bit more before I do general. I did like the problem statement. That was helpful, and I enjoyed seeing that, and not seeing the suffering, but in seeing that you had tied that in. I thought that the guiding principles were good, and I think those, you had guiding principles, goals, and then strategies. That was all really good. And I was glad that you mentioned sand scarcity. I think that is I think most people don't realize what's happening right now, that we have sand mafias. I know in India particularly, sand is very short right now. So finding an alternative to glass, even though glass, and you acknowledge this, glass is very recyclable. That was great to see the alternative, and I thought that was a good one. Rob, I have a couple more, but I'll take turns with you.
Sure. So I'll start at the beginning of the presentation. The exigence that you've added was great, and it was very personal. It was very powerful. So it really drew us all in immediately. Your use of the phrase, I think you came up with this yourself, I'm not sure, but we're in the same storm but not boat. That was really good. And I thought as I said already, your presentation is much clearer and powerful compared to your practice presentation. You sounded so much more confident with what you were saying too. So Professor Fleming, I'll tag team with you. You can go ahead.
Yeah, I was happy to see the last part at the end, because I was like, oh, she's reading her thesis statement again. She's done. And I was like, I wanted a little bit more, and then you gave me more. So
Yeah,
what I really liked was the look at 2050 and then the ultimate carbon negativity. And I think, that's what's going to differentiate you from other, say, engineers or folks that work on this, is that you do have a broader global perspective on what this means, and you're able to communicate to folks why it really matters. And getting to carbon negativity, that was a great series of slides at the end. So I really appreciated that. It made me feel like you had really completed the task and brought it full circle, so to speak.
Yeah, so that was one of the things that you really clarified since last time, because it wasn't clear why you even were talking about 2050, and now you really, I think you nailed it.
Yeah.
Can you hear me? Can you hear?
We can hear you. Yeah, we can hear you.
Sorry. Yeah, go ahead. I thought I accidentally hit mute.
I do think in optimism, I think you definitely should and are ready to present to revision what you did. I know you're probably nervous about that, but you do have to bring that full circle. I think you're ready for that. We can either send them this recording or you could present again. I recommend you present again live. I think it's a good career development for you, and you should take advantage of that. Plus, you might get a job. You never know. So, got to take risks, right, to get rewards. So.
I thought the scorecard on the right is so much better than what you were using last time.
Yes.
So much better, so much clearer. So that's great. Although we have some ideas on how to make it even better. But wow, that was great. So the use of the video simulation was great. The conclusion, as Professor Fleming mentioned, was clear. And I think it showed the depth of your analysis and the research. And I think you met your personal goal of rising, as you said, to meet that our profession has this duty to rise to this occasion and tackle these issues. And I think you're doing that.
Thank you.
Yeah, and I think just to make it a little bit bigger scale, I mean, I think you took a big risk in going to Disney for 2 semesters against the will of your program director, who only wanted you to go for 1 semester. So congratulations. I think it's sometimes good to push the boundaries, and I think you are a person who can push boundaries and should push boundaries. And I do maybe see you I hate to say it, heading for a PhD. Your knowledge and research and the way your career is moving, you might want to think about doing that, and we'd be happy to support you in that, which would be pretty exciting.
Yeah.
And finally, the last thing is that the biggest thing we look for is that have you achieved topic mastery? And I think you absolutely have. So that's awesome.
Thank you.
Yeah, I mean, I could see you right now. You're young, right? Where you are now with your age, in 10 years, you could be a national or international expert in circularity without a doubt if you continue to take risks. And so I encourage you to get yourself out there and try to get as many opportunities as you can. And we'll be lucky to say we knew you when, or we knew you when, right? Later in life. So that'll be pretty exciting.
I forgot to mention, I'm optimistic. You finished in 33 minutes. Sorry?
I was saying that was a huge compliment.
Yes.
Not a problem. 33 minutes, Rob. I was also happy.
33 minutes. Yes.
I vote that we revamp the thesis to a 35-minute time limit instead of 40. I do.
I don't think people can do it.
I think they can. I think you push. It's like the 4-minute mile. You push them. Surabhi, great to have you as a student, and appreciate all the work you've done. I know that you have some. Unfortunately for you, have some other things to take care of after this. So we'll be chatting about getting you out of here and graduating you with a high GPA. So.
All right, I'm going to pause the recording now, and Professor Fleming and I will talk about how well you've done in just a second. All right, Surabhi, congratulations. You have passed the first of your 2 steps. So we'll still be working together on the paper, but excellent job.
Thank you.
Congratulations.
Hey. Rob, I'm going to switch my background and get confetti streaming down when I come back on the next one. So I don't know who's next, but I'm going to try to find a better celebratory background.
Niranjan, please go ahead and share your screen.
I'm going to take a quick bathroom break, Rob. I'll be right back.
Sounds good. Okay.
Yep. Just in 2 minutes.
Surabhi, can you stop sharing yours, please? Great job again.
Thank you.
No, still, I think. We are still recording, I think.
Thank you.
Yeah.